So if you've looked at the schedule for the class, you'll see that there's certain lectures that are sort of thoughtful considerations of this and that, but then there's sort of some systematic chunks. So it begins with a couple of lectures about the cosmos, and by the way, I've changed the order just slightly. That'll happen again and again. But at any rate, there's a couple of lectures about the history of the cosmos, the first of our regimes, and then after a while we'll do some lectures about the history of the Earth. And then we'll do some lectures about the history of life and then the history of humanity. So what we're doing today is starting with the history of the cosmos. In particular, today I want to show you what is out there that we would like to understand historically. And to tie it into the first lecture of last Tuesday, I'm going to ask the question, where did the copper and the tin come from that went to make that bronze? And I just realized now I should invite the saber-toothed tiger to come up and be an example of a bronze statue. We'll try and put that in next week. Okay, so I'd like to begin with a vocabulary question. How many of you from time to time, amongst yourselves, maybe not talking to a professor, but with each other, use the word awesome? Anybody here ever use the word awesome? I kind of thought so. All right. So what I'd like to do is to ask you, what does the word awesome mean to you? This means, well, when you use it generally, it's just kind of something that's sort of neat, right? It probably doesn't mean that it is something that is so overwhelming that it inspires you with fear. That's probably not what you mean. So here's a couple of definitions. The dictionary definition of awesome is impressive and frightening. So impressive or overwhelming as to inspire a strong feeling of admiration or fear, as in the awesome destructive power of a tornado. You're probably using it in the second slang sense, which means excellent, used as a general term of enthusiastic approval. Is that about right? I think so. Okay. Like the second track on this CD is totally awesome. Not just awesome, but totally awesome, right? Okay, so what I'd like to do with you today is to show you something which is utterly awesome in the first sense. So impressive or overwhelming as to inspire a strong feeling of admiration or fear. When I hear somebody say the second track on the CD is totally awesome, I think, man, you haven't looked up in the sky. You don't know what awesome is. So that's what this lecture is about. It is to show you what's there. And then on Thursday, we're going to talk about the history of how that got to be there, everything that's up in the sky. Because remember, one of the points of this course is to get you in the habit of thinking historically about things, what I like to call historical mindedness. Whatever you're confronted with, you try to ask yourself, how did this come to be? What happened historically to make this come to be? All right, so here's what we're going to do today. First of all, I want to open your eyes to the unfathomable vastness of the universe. And then second, to develop an example of thinking historically by asking how particular resources on the earth came to be, in this case, copper and tin. And then finally, to prepare for what we're going to do on Thursday, which is to look more generally at the history of the cosmos and what has happened from the time when the Big Bang took place until now, or at least until the earth came to be. Remember, the earth is 1/3 as old as the cosmos. Exactly 1/3. Remember that? Okay. So here's the plan, and I'm sort of repeating this sort of layout just to make sure that it's clear. First of all, we're going to look at some of the objects that are out there in the cosmos, stars and planets and things like that. Just see what is out there that needs to be explained historically. And then we're going to look at the immensity of the cosmos. I want to try to get you, if not to be able to wrap your mind around the size of the cosmos, at least to have a sense of awe for it. And then we'll go and look at copper and tin. All right, so here we go, objects in the cosmos. These images all come from something called APOD, Astronomy Picture of the Day. How many of you ever looked at that on the web? Okay, if you don't, just go and Google APOD, and you will find every day there's a different astronomical picture taken by a telescope of some sort, usually a telescope, and they're just absolutely fabulous. And they have, each day there's a caption. If you just made it a habit of looking at that first thing in the morning or just before you go to bed, you will really get an appreciation of what astronomy is about. They're just wonderful. So I want to show you some of them now, and they don't come in any organized order. They're just whatever's cool and awesome for that particular day. So what I want to do is to show you some objects that are out there in a sort of a systemized way. So let's start with the sun. So here's our local friendly neighborhood star, without which none of us would be here. And there are lots of ways that astronomers can look at a star, or at least look at a close-up star like this. This is the only one that's close enough to see in any detail. But here's what it looks like in ultraviolet light. And there are all of these different little convection cell patterns here. So what's happening is that as in a pot of soup on the stove where it's hot at the bottom and you get it rolling over in a general boil, that's what's happening on the surface, in the near surface of the sun. Deep in the sun, it's hotter, and great vast masses of gas come rising to the surface, and I'm not sure, I don't know exactly how to interpret this picture, but probably the lighter ones are the rising hot stuff, and the dark parts are the ones that are relatively cool and sinking. So we see a bright ball in the sky that we can't look at and stay looking at, without damaging your eyes. But if you look at it with instruments, what you find out is that there's all sorts of complex structure there on the sun. And for scale, I would imagine that the Earth is probably about the size of one of these dots in here. Looking at it with a different instrument, you can see that every now and then the corona, which is this part that's outside, which here is barely visible, here there are great flares that come off. This is gas that's streaming out of the sun into the solar system. And every now and then a huge mass of the corona just comes loose and flies out. When these things happen, there are warnings given, because these affect telecommunications, and they're really hard on astronauts who might happen to be out there. So at any rate, there's all sorts of activity going on there. Here is another view of something. This is the surface of the sun, and you can see these vast sweeps of hot hydrogen gas, or actually plasma, which is gas that's so hot that the electrons are detached from the nuclei of the atoms. But again, the Earth is probably a little bitty thing in there. And here's a view of the corona. This is kind of neat. This is a picture that was taken at the South Pole when there was or in Antarctica at any rate, when there was a total solar eclipse. So this is the body of the moon, which happens to be the same size as the Earth, as the sun when you see it from here. And it just happens to be in front. So it's blocking out all this brilliant part here that you can't look at, and it's allowing you to see the corona sweeping out like a whole sun diameter out beyond it. So this is what a star looks like. And this is a garden variety star. The sun is a star of no particular distinction, except that it happens to be our star, so we care about it. But the sky is full of stars like this. All right. And surrounding it are planets, which are dinky in comparison to the sun. And here are some of them. Here's Mercury, which is very close to the sun, and so it's blasted all the time by intense heat from the sun. It also has on it various impact craters. And in fact, when you look at objects in the solar system, with rocky objects, with the exception of our Earth, they are just pockmarked by craters. So it's clear that if we want to think about the history of the solar system, there have been an awful lot of impacts in that history. And there you can see some on Mercury. Okay, here's Venus, and you can't see this surface with your eye because Venus has this enormous deck of clouds. There's no way to see through that with visible light, but you can see through it with radar. And so there are radar images now. There have been radar satellites put in orbit around Venus. And you can see all of these sort of weird circular things that are called coronae, which means crowns. And nobody understands them yet. It's pretty clear that there is no plate tectonics on Venus. But on Venus, there must have been an episode of what has been called resurfacing. And so Venus doesn't have its original surface. It has some younger surface. Nobody quite knows how this happened. But this is a sort of a scary concept. Supposing that the Earth resurfaced itself, it would not be good for creatures like us that live on the surface. Probably nobody's living there because the temperature is enormously hot and the atmosphere is acidic. But at any rate, you can tell that it's been resurfaced because there aren't nearly as many craters there as there ought to be. So that surface is not as old as the solar system. It's much younger. Get what's going on here? Each one of these objects is different. And each one of them has its own history that has led to it being the way it is. So here's Mars, for example. Now Mars has this enormous set of equatorial chasms that run across here. And clearly water was important in the early history of Mars, but it's essentially all gone now. Maybe some is left, but not very much. But Mars has an atmosphere, a very thin atmosphere. It's farther out than we are, so it's very cold. It's the only planet that we have any reasonable hope of going to and colonizing. Do you know the term terraforming? Have you heard that? Terraforming means to take another planet and somehow fix the atmosphere and fix the water and make it so that it would be inhabitable to human beings. It would be a terribly difficult job on Mars, but it's the one for which it's least conceivably feasible. You're not going to terraform this place. And then there's ones like Saturn's with their rings, and that ring is made up of just countless little asteroids that are all in parallel orbits going around there. It's not a solid ring. It's a plane of debris out there that's circling. So we looked at our sun, we looked at planets. Now what else are we going to look at? Well, let's look at our planet. So here is our delightful planet. Yes. Oh, thank you for asking a question, Matt.
Sure. The rings around Saturn, you
yeah.
said it was tons of small asteroids.
Yeah.
When you say small, do you mean like fist-sized rocks or car size?
In that range, in that probably a whole range of them, but they're all orbiting around there and they're all in pretty much circular orbits, because if they get out of a circular orbit, they run into the next one and they kind of get banged back together.
Asteroids of their own size?
Well, no, not with the ones their own size. They will stay with the ones that are the same distance out. Supposing we're looking down, you're looking down on Saturn now. So here's the planet. If there's an object out here at a given distance from the center of Saturn, it goes around at a certain rate. The ones that are farther out go around more slowly, and the ones that are in farther go around more fast. And so there's constant, there's always a shear, as it were, between this bunch of planetesimals, they call it, for the little tiny things, and the next one's out. But they pretty much have to be circular in their orbits, or collisions will circularize them. That help? Yes. Do ask questions. Thank you. Yeah, Danielle?
I'm a little fuzzy on the Venus resurfacing thing.
Yeah.
What happened there?
Nobody knows. It's all you can say is that the surface of Venus is not as old as the planet, because if it were, it would be absolutely covered with impact craters. And it has very few, so something has happened to give a new surface there, and it's a topic of research right now.
That's bizarre.
It is bizarre. You're going to see stuff today that's so bizarre. Yes. Awesomely bizarre. Yes.
Yeah, I think you said Earth is 1/3 the age of what, universe?
That's right.
Now, how about the other planets?
Our entire solar system formed at the same time. The sun condensed out of a cloud of gas. We'll see that Thursday, with all of the planets going around it. So the solar system is, remember that number, 4.567. That's easy to remember. 4567. It's 4567 million years ago. So all the planets are the same size, and so are all of the asteroids. And so the reason we know that is that meteorites that have been out in space for the whole history of the solar system sometimes fall on Earth, and you can date those, and that's where that really strong number comes from, 4, 5, 6, 7. Yes. Yeah.
You said there was no evidence of tectonics on Venus.
That's right.
Is there on
You know, that was such a surprise. In the late 60s and the early 70s when geology had the plate tectonic revolution, that was just the time when people were starting to get the first images of the other planets. And there were a lot of people, and I was one of them, who thought, oh man, we'll just be able to go and see the plate tectonics on all the other planets. We're the only one that has it. And nobody really understands why that is. On Venus, it may be because the surface of Venus is too hot. Venus has this enormously thick atmosphere that's mostly carbon dioxide. So if you think we have greenhouse heating here, imagine Venus, and I don't remember what the surface temperature is in degrees, but I do remember that it's hot enough to melt lead. And when the Soviets sent their spacecraft to Venus, the spacecraft took pictures of the area around them for, I don't know, a few minutes, an hour or so at most. And then they were just wrecked, partly by the heat and partly by the sulfuric acid in the atmosphere. It's a nasty, nasty place. Yeah, Deb?
Are there any moons of any of the planets that have plate tectonics?
There are 4 big moons surrounding Jupiter, and a couple of them have icy crusts, which show some evidence for cracking, which is vaguely like plate tectonics. But as far as we can tell, full-blown plate tectonics like we have on the Earth is only on the Earth. It's the only place we've ever seen it. Yeah?
So that the Earth had fewer impact craters than other planets?
Earth has very few impact craters, and the reason for that is that it's very active tectonically. It keeps churning over. It isn't as if it all got resurfaced all at once, but the Earth keeps getting resurfaced a little bit at a time. Remember, seafloor spreading makes new ocean crust. And the other thing is that erosion and sedimentation are so prevalent on the Earth that craters that were here will have been eroded away or covered over. There's something like, I forget what the exact count is now, but something like we know about 120 or 130 impact craters on the Earth.
So could this also be due to our atmosphere? And so is some of the smaller?
Absolutely. The atmosphere is what makes it possible for the surface of the Earth to be eroded and for sedimentation to take place.
So then, and you said that Venus's atmosphere burns melt lead. So how do we know that a bunch of the asteroids didn't just melt before they were able to hit the planets that would have hit?
You know, this is a question this is a really good line of questioning. I'm realizing that some of the things I said I'd want to think about more carefully. For example, when I said that Venus has been resurfaced, well, in a sense, so has the Earth, but maybe in a different kind of a way. I don't think that the heat of the atmosphere would burn up an asteroid because they come through so fast that they are on the ground before they get burned up. And there are some impact craters on Venus. They're quite spectacular, but there aren't very many. Okay, great. That's good. So let's go on now and just look at our planet here. I think we're all so familiar with this. Here's what the moon looks like. Now, this is a really dead planet. This is so small that it has no atmosphere at all, and it has its internal heat is pretty much used up, so it doesn't do plate tectonics. It just sits there. And about the only thing that happens on the moon is that objects hit it. So this is a collection of craters. See, these are big old ones. There's a smaller, moderate size. But if you look at the surface of the moon, it gives you some idea of what the density of cratering is for an object that has been sitting there as a target ever since the beginning, right? Okay. Now, I want to particularly focus on this picture down here because this is a picture that is full of meaning, I think. Can you see inside the circle? The circle's just drawn there to show you where to look. There's a pale blue dot in there. And this is the Earth. And so what I'm going to do now is to show you what Carl Sagan wrote about this, because this picture was taken by NASA at his request. Carl Sagan, the great astronomer. So just let me read this. You might want, it's in there and you can read it later, or you'll get it on B-Space, but you might just want to listen. Just maybe think about that picture, and I'll read it to you. So Carl Sagan asked NASA to make an image of the Earth from the Voyager spacecraft, which then was at the very edge of the solar system. And here are Carl Sagan's thoughts. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all of those generals and emperors so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Okay, so let's see what else is out there. So there are stars. There are vast, countless numbers of stars. And so here is one that you can actually see with your naked eye in the sky at night, the Pleiades. How many of you have seen the Pleiades? Okay, you can usually see about 7 with your naked eye if you have good eyesight. But there are other clusters. This is a globular cluster. This is more than 10 million stars, all close together. They must have all formed together and then never really moved apart, although the ones on the outside are probably drifting apart. Interesting to look at this and say, how do they stay there? Think of this as a colossal number of stars, 10 million or so, and they're all orbiting each other under the influence of gravity. So imagine the complexity of the orbits who are there. Those of you who've taken physics know how hard it is, how impossible it is to solve the 3-body problem. Imagine your homework assignment was to solve the 10 million body problem. So these things are out there. And it's just part of, well, we'll see, it's part of a galaxy. We've now been able to see new stars forming. This is a famous picture that NASA took with the Hubble spacecraft, and inside, this is a cloud of gas. Inside the cloud of gas and molecules, a new star has formed, and it's just lit up, and the pressure from that star is going to clean out. It's going to blow away the gas that's around it and leave it open. This was probably inside the cloud not so long ago, and it has cleaned out around it, and this cloud of gas has another star in it that's just about to blow it away. So we can see stars forming. The cosmos is very dynamic. New things are happening all the time. New stars are forming. Josh?
On the slide before the globular cluster,
Yeah?
how close are those stars with one another that are in that?
I wish I knew, but I don't. I would imagine the whole thing is probably like a few light years across. Is anybody astronomer who knows that? We may have, if there are astronomers in here who may be able to contribute, yeah?
Yeah, they're usually on the order. I don't know which one that is, but there's probably like around 10.
Okay.
Across,
Paul's,
like our galaxy.
okay, Paul says 10 light years across. Okay. Okay. Okay, and then this is the formation of new stars. This is the destruction of an old star in a supernova, and I'll leave that because we're going to come back to that later. Okay, so stars are not spread evenly throughout the universe. They're clustered into galaxies. Know where the word galaxy comes from? It has to, it comes from Milky Way, because L-A-C is in lactose, is in milk. So the first galaxy that we knew about was the one that we're inside of. So that's the Milky Way. This is the nearest big one to us. This is Andromeda, which for a long time was thought probably to look very much like the Milky Way. We don't know what the Milky Way looks like with any detail, because we can't get outside it. We're inside it, and you can't get outside it and look back at it. So it's hard to figure out what it looks like. But people used to think it looked like this, with a big central cluster of stars in here, and then these rings, maybe these sort of spiral rings like that. They now think it may have a sort of a bar across here, and then the spiral arms start out at the end of this bar. So we don't really know what our own galaxy looks like. This is the nearest big one, and these galaxies are colossal numbers of stars. Look, they have typically about 10 to the 11th stars in the galaxy, one followed by 11 zeros. That's 100 billion. So we know one star real well because it's close by. But our own galaxy has 100 billion of these things in it. You see what I mean about awe? How many galaxies do you suppose there are? Again, something like 10 to the 11th galaxies. Maybe it's more than that now. So we live on this tiny speck of the Earth. And it's much more awe-inspiring than what Carl Sagan talked about, because he was just talking about seeing the Earth from a spacecraft that's way out on the fringe of our solar system. But our solar system is one of 100 billion stars in our galaxy, and our galaxy is one of 100 billion or so. Other Josh, yeah?
How big would you say the average star is?
They have a wide range in sizes. The sun is in the sort of slightly toward the smaller end. And the smaller the star is, then the less pressure it makes on the center, so the nuclear reactions don't go as fast. So the small stars are kind of red and relatively cool compared to ours. And then they go out to enormously larger and very much hotter ones than that. And in terms of sizes, I'd have to go and look it up. I don't know the numbers on it. Okay? Thank you for all the questions. That's great. Okay, so here are two examples of galaxies. This is a wonderful picture. This is two galaxies which are in the process of colliding. And probably no star in there will ever hit another star because they're so far apart. But as they go through, the gravitational disruptions will tear the whole things apart. And so people have seen galaxies that apparently have gone through collisions, and all of that beautiful spiral arm structure gets completely screwed up in it. We don't have anything coming at us right now. You'll be glad to hear. And yeah, oh sure.
If they collide, do they kind of recalibrate themselves after?
That's a really good question. That would be my first guess. That would be my non-astronomical guess. Would be that they would break themselves up, destroy their structure, and then over time they would generate new structures. That's a really good question, because we'll see later that when you, and maybe it's Thursday, you'll see when you look at really old galaxies, you can see them, they're very, very far away, so the light has spent most of the history of the universe getting here. The oldest galaxies are very irregular. They don't have spirals in them. So clearly the spiral is something that grows through time, and I think that's a very good intuition you have.
And do you think like stars would transfer from like potentially from one to the
Oh,
other?
I would imagine. In fact, it might be hard after the collision to tell which one was which to begin with. In fact, it might just turn into one great messy blob. I think there are people who work on this and are studying this right now. Yeah.
I'm just curious, maybe if I heard wrong, but I don't know if you mentioned that we can't see galaxies.
That what?
That we haven't seen a galaxy or something.
Did I? What did I say that? Because
Our own galaxy.
we can't see our own galaxy because we're inside it. Thank you. Yes, that's right. Okay. Yeah. One more, and then we'll go. Yeah.
How much do galaxies, like, how much do they move? Like, the whole thing? Like, are they going away from us, or like going together?
Okay, that's a great thing that we'll come to on Thursday, but basically, in general, everything is moving apart. The whole universe is expanding. So, to first approximation, you might say that all other galaxies are moving away from us, except that there are clusters of galaxies. See, this is a cluster. All of the salt grains in here, it looks like, those are stars in the foreground. But if you look out here, these things are all galaxies that are very close together. Each one of those things has, maybe 100 billion stars in it. Who knows? But at any rate, they are all attracted to each other gravitationally. So within any cluster, you can have galaxies that are moving toward each other. So in fact, we're in a smaller cluster, not as big as that, but with Andromeda and the Magellanic Clouds and some other galaxies, some of them are moving toward us. So that's why you can have a collision. But on the broad scale, thanks, that really cleared that. On the broad scale, things are moving apart, and we'll come to that on Thursday. Okay. All right, so that's what's happening. One more, Josh.
When we're looking out at the night sky, do we see stars only in our galaxy, or do we see stars outside our galaxy?
You can see almost everything you see is a star in our galaxy. But the early astronomers, when they were looking with the naked eye and then even with the telescope, the early telescopes, they would occasionally see a fuzzy patch. Stars aren't fuzzy, they're little points of light. And they would see these fuzzy patches, and they called them nebulas. And so a nebula is the same word as cloud. They sort of look like cloudy patches of light. But they were big compared to a star. The close-in ones were. And they turned out, when the resolution of the telescopes was better, they turned out to be galaxies which were vast clusters of stars. But when you see a point of light in the sky, it's either a star in our galaxy, or in a few cases you may be seeing a whole galaxy at a great distance. Good. Okay. So now let's turn from what is out there, what objects are out there, and I want to try to impress on you the immensity of this thing, of this universe we live in. I think I may have said maybe last week that it's very hard to wrap your mind around the time scales that are involved in big history. It's equally difficult, maybe more difficult, to wrap your mind around the scale of the universe. So let's try. There's some astronomers recently have made some nice tools that help with this, and I think we're going to go on here. Roland, bless his heart, has made some has turned some of these things into videos. So, is this the one I just showed? Yeah, lower right, there's the Virgo cluster of galaxies. There's the Virgo cluster of galaxies again. And this is a simulation, and you'll find this, you'll be able to see on the bottom, there's a website, so you can go back and look at this on your own if you'd like to. And so what it says there, this is a simulation of a flight from Earth towards Orion. Remember, Orion is a constellation in the night sky. Passing the young stars of the Orion Nebula, the Horsehead Nebula, and these nebulas are actually clouds of gas. They aren't distant galaxies. And we're going to pass the Rosette Nebula and the Crab Nebula, which is the supernova remnant we've looked at. Then, rising above the plane of our Milky Way galaxy, which of course we can't do, so this is a fake. Rising above the plane of our Milky Way galaxy, we see our entire galaxy, then the two Magellanic Clouds, which are small companion galaxies to the Milky Way, then our great twin, the Andromeda Galaxy. Finally, we'll travel towards the huge cluster of galaxies in the constellation Virgo. Now, remember, this is something you can't do. Nobody, I think I'm safe in saying nobody will ever be able to do this, because we're going to be moving at far faster than the speed of light, which, as far as we know from physics, is a fundamental limit to how fast you can ever go. This is a computer simulation. The way it's done is by measuring the distance to all of these objects, and astronomers do this in sort of, they have mass programs to determine vast numbers of distances and just to different objects. And then it's all put into a three-dimensional computer simulation, and then in the computer simulation, you can fly through it as fast as you want. So what we're going to do is go on a journey that nobody could ever take. But what it does is give you a sense of how vast things are. Thank you, that's good. Is there, hopefully this, let's see if this works now. Okay, so here is the picture. Now what I'm going to do, I'll try to run this through twice. And first of all, I'll tell you a little bit about what we're doing. The second time I run it through, I'll try to just be quiet so that you can enjoy it yourself. So here we go. Is it moving? Not yet. There we go. Okay, now every one of these specks that looks like a snowflake in a snowstorm in the car headlights is a star. We're inside our galaxy. And in fact, that band is the plane of our galaxy looking out. And now we're coming, I think this is the Orion Nebula with gas in there and moving on. So there are all of these things out there, these great clouds of gas in our galaxy, in amongst this incredible collection of stars. And who knows, as that star goes by, maybe that star has a solar system, and maybe it has a livable planet. Maybe there's life there. Another cloud of gas going by. And now we've sort of changed our orientation. There's the Milky Way. So this is bright, not because it's the clouds, but it's just an absolute mass of stars in there. Remember, there's 100 billion in our galaxy. Okay, now we're going to climb up out of the plane of the galaxy, and we're looking here at the center where the stars are clustered more closely than they are where we are farther out. And there's a spiral ring. Obviously, this is an image of another galaxy, someplace that they've used as a stand-in for ours. There go the two Magellanic Clouds, which are close to ours. Other little galaxies in our cluster of galaxies. Remember, every one of these every one of these galaxies has hundreds of billions of stars in it. We've just passed through that galaxy. Now we're out into space. You see, now every speck you're looking at is no longer a star because we're outside our galaxy. Every speck is a galaxy. And this is the Virgo cluster. There go any number of galaxies just going past. And then in between the clusters, there's a cluster. In between the cluster are areas that have very few galaxies in them. So the structure of the universe is kind of sponge-like, with areas that have lots of galaxies and areas that don't have so many. He's kind of flying around the Virgo cluster right now. Every one of these is a galaxy with uncounted stars in it. And this is one cluster of galaxies. There are vast numbers of clusters of galaxies. Okay, I'm going to run through it once more if I can, just to let you look at it quietly. Let me see if I can figure out how to do this. Maybe there. Okay, here we go. Let's try this. Okay, I want to stop now and go on because I got more stuff to show you, and hopefully we'll go on. But yes.
How fast were we moving?
You know, I imagine that when we were inside the Milky Way at the beginning, we were moving relatively slow because we were within a single galaxy. Then it must be speeding up as it goes outside because you can see one galaxy after another. Yeah, Michelle?
So all of the stars are clustered with galaxies. So at the beginning of, let's say, the universe, was the stars not clustered?
That's a really good question. Were the stars clustered to begin with? My understanding of it is that the hydrogen gas that went to make the stars was itself clustered first, so that you had massive clusters of hydrogen gas, which then became galaxies and clusters of galaxies and stars within those. I don't think you should think of the stars as being there first. and then clustering into galaxies, but rather the material that the stars were made from being clustered first. And that's something actually, it's quite a hot topic going on right now. I want to show you one more. So this is something called the Hubble Deep Field. So the Hubble telescope takes these incredible pictures. And there's a man named Steve Beckwith, who's now the vice president for research of the whole University of California system. And he ran the Hubble Space Telescope Institute. And as the director, he was able to take a certain amount of time and do something interesting with it. And so he did something that most other people didn't like. They wanted to take pictures of stars and planets and galaxies and things. He said, I want to go to a place where there are no stars and just see what's out there. And so they found a place in the sky where there were very few stars. It's hard to do that because we're inside this Milky Way galaxy that has so many stars in it. But they found a direction where there's only a few distant stars in it. And they just turned the telescope there, and they kept it there for a long time. They accumulated light, so they were seeing absolutely what is the most distant things there are in the whole sky. This is called the Hubble Deep Field, and then they actually went on later and they did the Hubble Ultra Deep Field. But this is what they got. And this has got, let's see, I think that there are no nearby stars. I think that's a nearby star right there. You see sort of the crosshairs from the, that's a nearby star in our galaxy. Everything else that I can see in there right now is a distant galaxy. And they're so far away that they had to leave the telescope accumulating light for a long, long time in order to even see what's out there. So this is presumably, this is not chosen in any special direction except a dark direction. So presumably this is everywhere. So all the way around the entire surface of a sphere surrounding us, anywhere you looked, this is what you'd see. Every one of those is a galaxy. And now there is a fly-through of this that's been made, and here it is. And so what you're going to do here, they've been able to measure the distance to each one of these galaxies. You do it by redshift, as we'll talk about later. But at any rate, they've again made a computer model so that you can zoom through this and see what's going on. So now just watch what happens as we go farther and farther out. We're just going to go straight into this, oh, sorry, wrong one. See if that makes it go. It takes a moment to start to move. Is that moving? Oh, maybe I have to click there. Let's see. I'm not seeing the arrow on the screen. What's going on here?
Well, push the cursor all the way right, get it onto the projector, then click.
Oh, there it is. Thank you. That's it, Roland. Good. Okay. It's going now?
And then wait, there's the cursor.
Yeah, it takes a moment for it to speed up and get started. Do you think I have to be on the image? There it goes. Okay. Now you can see we're moving in. So these are the closest galaxies to us in there. And remember, this is a tiny little pinpoint speck of the sky that we're looking at. And these galaxies are so far away that their light has taken nearly the age of the universe to get to us. So we're not seeing galaxies as they are today, we're seeing galaxies as they were when the universe was very young.
About how many galaxies did they count?
Well, a few years ago, the estimate was 100 billion for the entire...
Just that one spec?
No, for the entire universe. I don't know how many there are here. Do you know, Paul, how many there are?
Just in the deep field, I'm
Yeah.
not sure.
Yeah. Uh-huh.
Are the spirals developed like after the galaxy emerges?
Yeah, the question is, when did what spirals develop? One of the things that you can see in the Hubble Deep Field, and maybe not here, but in other things, is if you look at the oldest galaxies in there, which are the most distant, the ones that whose light has taken a long time, they're blobby. So the spirals started forming, maybe 2 or 3 billion years after the beginning of the galaxy. So the spirals have gradually grown through time. I'm going to have to move on here because I've got another thing to show you. There's more stuff in here that you can find. By the way, the handout is for you to take notes on. The PowerPoint will actually be on BSpace at some point, and you can play with it there. But what I want you to do now with the rest of the time is look at the rest of the historical question we started out with on the first day a week ago, which was where did the copper and the tin come from that made the Bronze Age possible? Okay, so what we saw then was thinking as a geologist, you can say, well, it came from black smokers on the bottom of the seafloor where seafloor spreading took place. But I briefly mentioned at that point that the next question is, how come there's any copper and tin at all? Because when the universe was very young, it had just formed in the Big Bang, there was hydrogen and helium. And everything has formed since then, and that's what we're going to see. And since I see a few yawns around, this would be a good time. Don't talk to anybody. Take a few moments just to stretch and get your focus back. Okay, everybody ready? Here we go. Rest of the question for today. Okay, so here's what we're trying to explain. The bronze that was worked in the Bronze Age by humans, say around 2000 BC, something like that. And our question, where does it come from? Remember how useful bronze is for killing people and things like that? All right, so I'd like to start this by a kind of a geologist's view of nearby objects. So here on the upper right is the sun, and the sun is completely different from the moon, which is down in the lower left. There's Earth in there someplace. But the difference is that the sun is made of gas and plasma. It's made of hydrogen with some helium in there. And the moon is made of something completely different. It's made of dominantly the elements silicon, oxygen, magnesium, and iron. And when we talk about the history of the Earth when we're talking about Earth history, we'll see how planets like the Earth and satellites like the Sun came to have this composition of silicon, oxygen, magnesium, and iron, why they have that and the Sun has hydrogen. But the real question here today is where did those other elements come from? Because this, hydrogen and helium, that's what's there when the universe first formed during the Big Bang, and all the rest of the stuff has come, all the other elements have come into being since then. There wasn't any in the early universe. There was just 0 iron, copper, and tin in the early universe. How did that happen? So, question, how does nature make elements heavier than the hydrogen and helium produced in the Big Bang? Okay, I'm going to show you now some nuclear physics, but I'm going to do it in a way that's fun. And I hope you'll enjoy this. I had fun figuring that out. You remember the myth of Sisyphus? Sisyphus was in Greek mythology, was a guy who'd been pretty bad in his life, and he was condemned to a very nasty afterlife. And his sentence was that he had to spend eternity rolling a great big rock up a steep hill, and he'd just about get it to the top, and it would come rolling back down, probably over him, and then he'd have to go out back and start it again. So that's the myth of Sisyphus, which is hard to say, right? And so I thought we could talk about the nuclear physics that goes on inside of stars and that produces iron and copper and tin. I thought we could talk about it in terms of Sisyphus. So here's how we're going to do it. So we're going to move Sisyphus down over here so that there's a room for the rest of this drawing. And instead of pushing a big rock, Sisyphus is going to be a really tiny creature now. And what Sisyphus is pushing is a proton, okay? And he's pushing it uphill, and it's really hard to push it up that hill. And Sisyphus doesn't know why, he just knows that there's a hill there, and it's harder and harder and harder. He gets it up a certain distance, and then it rolls back and rolls over him. You really wouldn't want to be run over by a whole proton, would you? Okay, but what Sisyphus doesn't know, because he can't see it, and we can, is that there's another guy over on the other side who's trying to do the same thing. He's trying to push it towards Sisyphus. And there's the slope that Sisyphus is going up, and on the other side is this mirror image, and we'll call him Brotherphus just for the fun of it. And these two guys are trying to push protons toward each other, and it's hard. The closer they get, the harder it is. And why is it hard? They repel each other. They have the same charge. They're both positive charged. And there is an electric force in there, and the electric force gets stronger and stronger as you get together. The farther out, the farther apart they are, the less the force is. And so the more these guys push these protons together, the more they're fighting against this electrical repulsion from these positive charged protons. That's why they have such bad time. Yeah? At least if they could talk to each other, maybe they could sympathize or something, but they don't even know the other one's there. Okay, so the next point is to say we can turn this into a sort of a roughly physics type of graph with distance there, and you have to put more and more energy in to drive these things up this steeper and steeper hill. And, well, they get some help. They're down inside a star, you see, and so they actually get help from this pushing, and they get help from the great pressure deep inside of the star. So it isn't just that they're out there pushing these things together. If they were, that's the end. You couldn't do it. But since they're inside the star, the pressure of all of the other protons in there is helping them push these things together. Okay? Now, another thing that they don't know is that there's another force in there that's going to help them. What's that? Anybody know what that is? That's the nuclear strong force. So there are two forces that are acting on these atoms. There's the electrical repulsion that keeps them from coming together because they have the same charge. But there's another force which is called the strong nuclear force, and here it is. What that says, if you're too far back to read, it says strong nuclear force, attraction. This pulls the things together, but it only acts over a very short distance. So two protons will repel each other intensely by their electrical charge until you get them close enough together that they come inside the range of that strong nuclear force, and then they jam together, because the strong nuclear force that pulls them together is much stronger than the electrical repulsion. But it doesn't work until you get them really close together. So that's what's going on inside of stars. And what happens then is if they can get up over the edge to the point where the strong force is helping pull them together, then they drop down into this what's called a potential well right there. So you can think of this, Sisyphus will be finished with his condemnation if he can ever get it up over the edge, because then the strong nuclear force will pull the two protons together and they'll be strong. What's that called? Nuclear fusion. So this is nuclear fusion. And the reason that it is so hard for nuclear fusion to become a practical source of energy is that it's just so hard to get protons past that, through that repulsion, that electrical repulsion, to the point where they will jam together and be stuck together. So did it ever bother you that inside the nucleus of an atom, you may imagine you've got a carbon atom. It has 6 protons inside it. Protons repel. Why are they stuck together in the nucleus? Why do they stay there? The reason is that the strong force is holding them together. Once they get inside that range, then they're held together, even though electrical repulsion would like to make them fly apart. Okay, so this is nuclear fusion, and this is what's going on inside of stars. Now, if you'll notice here, this level is lower than it is over here. Remember, this is an energy scale here. So it's this difference in energy that you get out, or we would get out if we were able to use nuclear fusion as an energy source. That would be the source of the energy. It's the source of energy inside of stars. So all of us are here breathing, we're eating our veggies and things like that, and the veggies grew because of energy that came from the sun. All of that is coming from nuclear fusion. And it goes at a moderate rate because the electrical repulsion keeps most of those protons apart. It's only a few of them down in the core of the star that can get together and fuse, release that energy. Then that energy comes working its way out through the star by convective overturn. Remember, the surface of the star was sort of speckled, and those were the convection cells rising and falling. And then that hot gas gets to the surface, and it radiates the heat energy that plants use and that we use when we get warm in the sun. So that's what's going on in stars in a sort of a way that's maybe more fun than the equations of nuclear physics. So I have a picture here that I'm not going to go into at all, but just simply to say, if you start with protons, there's a whole series of these events. This is a fusion event here, and there's a whole bunch. This makes one proton plus one neutron, and it keeps going together until you eventually get out a helium nucleus, which is 2 protons and 2 neutrons. And then if we carried it on further over here in this part of the blackboard, there are more protons being added, which brings it up to carbon, then it brings it up to oxygen, and it brings it up to all of the other elements, up to iron. So this is nuclear fusion, and it's the source of all of these elements that are heavier than helium, but are not heavier than iron, because that's where it stops. So here is the periodic table of the chemists, and here is element number 1 with 1 proton, element number 2 with 2 protons. Those were there. Those were made in the Big Bang. But after that, nothing was made through that whole dark period that I think O'Shea was talking about, in which it was before there were any stars. Somebody over here was, at any rate. There's a long time there where there's gas clumping to make galaxies, but stars have not yet started to form. Astronomers call this the dark age. Dark because there weren't any stars, so there wasn't any light being formed. So in that time, it's all still hydrogen and helium. And it isn't until the stars begin to form and begin to be big enough for that pressure to make fusion take place that you start to get energy out of stars, and you start to get all of those other elements that are heavier, up to iron. So we're looking at a process here, the process of nuclear fusion, and on Thursday we'll see what this tells us about history. How has the history of this been? The history of this process been through time, and what has it done? So anyhow, here's hydrogen and helium from the beginning, and all of the other elements here, lithium, beryllium, boron, some of you know this by heart, all the way out to argon, all the way through here until iron, they can all be made in this way by fusion. And that's the end of the line. Because you can't go beyond iron with fusion, because if you add more protons to iron, it soaks up energy. It doesn't give off energy. So iron, you can think, this is a good thing to remember. Iron is like nuclear ash. It's like ash in your fireplace. You can't set fire to it and get any more energy out. You've gotten it all. So to go to heavier elements takes more energy to be added. So stars don't make anything heavier than iron, any elements heavier than iron. How do they get made? Who knows how they get made? I mean, obviously they're there because there's copper and iron and copper and tin and bronze. How does it get made? Yes.
Just to guess, would it be 2 different elements mixing to create more energetic?
That's a good guess. And in fact, it is elements that exist already that already exist, getting added together, getting combined. But the thing is that they don't get combined in this method. They get combined in a different way. The only way you can make them is to take the star and absolutely slam it together like that. In that case, all of those elements that are inside get slammed together all at once. And that's called a supernova. That's how the copper and the tin get made. So at the bottom, I've tried to put the headings at the top for you, but at the bottom it says, so how does nature make the elements heavier than iron, like the copper and tin that people use to make bronze? And come to think of it, if the elements heavier than hydrogen and helium are made in stars, how do they get out of those stars and into rocky planets like the Earth and its moon? Well, that's what happens in a supernova. Okay, now supernova is an awesome explosion in the real sense. It is an exploding star. And I'm not going to go into exactly why the stars explode. It's something I've tried to understand 2 or 3 times, and I get partway there, and then I sort of forget the details. It has to do with the star running out of fuel, but it runs out very rapidly. And so here you have this great star that's being held out as a big ball of gas by the heat inside it. I think the heat leaks away in the escape of neutrinos, and suddenly it's like it just deflated this ball of gas and it just slams together like that. So that's the beginning of a supernova. So a supernova explosion doesn't start with a blowing up, it starts with a collapse. And then, as everything falls together, I'm getting nods from the astronomers, I must not be too far off. Okay, as it collapses in the center, most of the material stays there, but some of it bounces out at very high velocity and goes shooting out into nearby space. That's a supernova, and that's going to contain all of the elements up to iron that were made slowly by fusion, but also the collapse itself has done what Josh suggested. It makes the other elements that are heavier than iron by cramming together things that are lighter than iron. So it's the collapse that supplies the energy that's needed to make elements heavier than iron. So all that goes on. And here's the life history of the sun. I'll pass over that because we're about running out of time. Sun is probably not going to go supernova. It's not the kind of star that leads to supernovas. It will get big. It will make a red giant, but it's not going to blow up. So here is the interior of the star. I'm going to move through this a little bit faster because I'm taking longer than I thought. I wanted to show you a couple of, maybe one animation, maybe 2 animations. So astronomers or physicists have also made these images of what a supernova looks like. And let me just show you a couple here that Roland put into video. So this is looking down on a star. Imagine now that we're sort of able to look at this star. And it shows here, oops, that was the wrong one. Here we go. There we go. Okay. Okay, now there it collapses, and it seems to be, and there's the bounce that throws all of this gas and dust out. You may have noticed that there was a tiny little ball in there in the center, which is the supernova remnant. Maybe a neutron star. It's very small. It's not giving off much energy anymore. But all of this stuff that got blown out. Want to see that again? Okay, let's do it once more. Okay, so you'll see the star collapse, and then there's a sort of a little bounce, and then a big bounce, and then at the end you'll see a big cloud of gas around it. In the center is the remnant of the star, which is now very small. There it's collapse, little bounce, big bounce. Now see the little remnant in the center, and all that yellow stuff around there. Now that's gas that's full of these elements that have either formed by fusion or have formed by being crammed together in a supernova. And here was one more. Let's just quickly show this and see what it looks like. There it goes. And as it cools off, then you can see the remnant in there. And this one was an attempt to model the formation of the Crab Nebula. And I'll show you that in a moment. Here is what a supernova looks like. They say that when a supernova goes off, it is brighter than all of the rest of the 100 billion stars in its galaxy put together. So these explosions are colossal. So this is a picture of the Magellanic Cloud, which is a small galaxy near us. And this is what it looks like. So you can see here's during the supernova. So you can see here's this particular thing. It's sort of, you can see all these here's this object is here, and that is the star which is about to become a supernova. And here it is when the supernova takes place. And this would be brighter than all of the stars combined in that Magellanic Cloud. So these are colossal events. Here's a very distant supernova. This is an image of a galaxy, probably a little satellite galaxy here. And here it is with the supernova going off. So various pictures of them. And this is what's left now of that great supernova that took place in 1987 in the Large Magellanic Cloud. So if you look at it now, this is the spot where the star was. And there's this strange pattern of rings, which maybe somebody understands, but as of the last time I tried to find out, I couldn't see a good explanation for it. There's a lot of really weird physics and astronomy going on in these supernova explosions. They're colossally horrible to think about. You wouldn't want to be anywhere near one when it went off. But we are only here because vast numbers of these supernovas have gone off in our galaxy from 13 billion years ago until 4 billion years ago when the Earth formed. They're still going off now, but when our sun formed, enough of them had gone off that there were elements heavier than hydrogen and helium all the way out to copper and tin. So what happens to elements after iron, after they're made and dispersed by supernovas? Well, they get incorporated in planets like the Earth, and then in the Earth there has been convection taking place and plate tectonics, and that's where the copper and tin came in. This is this plume of debris here, of fine particulates, is rich in copper. And when you think about it, this copper goes all the way back to supernovas, probably not just one, but many, many, many that mixed their copper and their tin and their uranium and all the other heavier elements, mixed them into the cloud of gas which eventually condensed to make the Earth. And so I think maybe I'll finish on this one. Here's our little crab walking around on the ochre on the bottom of the seafloor. And there's this huge historical story lying behind it. And on Thursday, we'll talk about what the whole history has, try to see the whole panorama of history in the cosmos. So enjoy your sessions with Ryan and David tomorrow, and I'll see you on Thursday.